Hello guys, we are doing coding patterns today, and we will try to cover actually two coding patterns. One is the two pointer and the other is the variation of two pointer, which is called fast and slow pointer. These were two considered relatively easy patterns, but there are so many questions that can be solved, especially the two pointer. And even some people will say sliding window is also a variation of two pointers. Generally these two coding patterns, they are used to solve questions related to arrays or strings or linked lists, you can say. So linear data structure in general. They are not involved with graphs or trees or stacks. Stack could be considered a linear data structure. Over there, actually, they can be used, but I have not seen any problem that uses two-pointer approach for stacks. But anyway, it's generally all the linear data structure. Generally, it's array or a string, and you use two-pointer to solve the problem that you're solving. We will try to understand this thing with the problem actually. Let's start with that, right? Jump into it. So this is the problem we have written. Given an array of sorted numbers and a target sum, find a pair in the array whose sum is equal to the given target. So we are given a sorted array and a number target sum, and we need to find a pair. It's very simple, very easy, but we were just trying to understand, get the feeling of this pattern through this problem. Let me actually do this thing on over here. This is my iPad. Can you guys see it? Can you guys see it?
Yeah.
Yes, we can.
Okay. So the 1, 2, 3, 4, 6. 1, 2, 3, 4, and 6. Okay. So this is the array. So we need to find a pair, any pair, which means with the given target sum. And what is the target here? Target is 6. Okay. So let's say our target is 6. So in a coding interview, I think the first approach that should always come into your mind is the brute force approach. And if you start actually understanding the brute force approach, a lot of things gets easier after this. And brute force approach is generally, you can say, it's at a very generic level. It's like trying all the permutation of the input to see if we can solve the problem, or we can achieve the solution of the problem by trying all the possible combinations of the input. In this case, we are trying to find a pair. So which means in this array, all the possible pairs, if we can somehow quickly find out how we can find all the pairs and see if any pair targets to 6, sums to 6, and then that's the solution. So try practicing this thing, that how to find out all the combinations of the input. That always lead you towards the brute force approach, and like it should start coming. The solution should start coming to your head within like a couple of minutes with practice. In this case, what does this mean? That take, for example, this one number and pair it up with every other number, which is like pair it with 2, 3, 4, and 6, and see if we get the target, which is 6. So 1 plus 2 is not 6. 1 plus 3 is not 6. 1 plus 4 is not 6, or 1 plus 6 is definitely not 6. Similarly, then we take 2 and we try to sum up with pair it up with other numbers. 2 plus 3 is 5, and 2 plus 4 is 6. So we found our solution. So this is the brute force approach, but I think the idea over here is try to understand how can we find out all the permutations of the input, all the valid permutations of the input. I would say valid over here means a pair. It's not like 3 numbers or 4 numbers or subarray or anything. It's the fixed pair, and pair can be of any 2 numbers. It's not the pair should be consecutive, or like keeping all the constraints of the constraints or the flexibilities of the problem in mind, and then trying to find out all the combinations and see. So how can we use it? We saw it, and it's like taking one number, matching it up with all the other numbers, and find and making it a pair and see if they sum up to target. Clearly, if you can see, since we are taking one number and matching it up with, pairing it up with all other numbers, and then take the second number, pairing it up with all the other numbers 3 and 4 similarly. So which means we have to iterate once for each number, which means order of n square. It's clearly very simple. I would take every number and match it up with every other number. So every number means order of n, and matching each number with every other number is also an order of n. It becomes order of n square. So brute force is n square. What else we can do? Whenever the array is sorted, the first thing that should come into your head is, can we use binary search? Because binary search is the most efficient searching algorithm on the sorted linear array, especially. So how can we do it over here? We have again 1, 2, 3, 4, and 6. So we take one number and search the other number in the remaining array, so that it can sum up to the target 6. When we have 1, so we need 5 to make 6. So we search 5 in the remaining array. So and that searching is log n, right? So take each number and search in the remaining array. Similarly, take 2, and this means we need the other number should be 4, and search 4 in the remaining array, in this array. So this means for every number we're doing a log n search. So n log n would be the time complexity, right? This is a little better than this one. You can say this one is like this. So order of n log n is better than n square. And space wise, there's no extra space. The top one has 2 for loops. This one has again 2 for loops. One is for iterating all the number, the other is for the while loop, a typical the binary search while loop, right? So there's no extra space. Both of them are using just like time and time wise. This one is better. So always think about this thing that, oh, can we use the binary search for a sorted array. So then comes this approach, actual approach, which is the 2 pointers approach, which says we can actually do everything in one iteration. So it says 1, 2, 3, 4, and 6. So generally, it says that we can use 2 pointers to iterate the data structure, in this case array, and most of the times 1 pointer is pointing at the beginning, let's call it P1, and the other is at the end, P2. And the idea over here is that we sum up these 2 numbers. This could be our probable pair, and if we see that we cannot achieve the sum by pairing up these 2 numbers, then we move our pointers, or like increase the beginning pointer or decrease the end pointer in an intelligent way. That's the whole idea. For example, over here, when we say 1 plus 6, which is 7, so 7 is more than the target, right? So which means we should reduce our sum, right? So reducing means only this pointer, P2, is pointing into the decreasing sequence of numbers, like 6, 4, 3, that is the decreasing sequence. and this P1 pointer can move in the forward direction, and the forward direction is the increasing sequence of numbers, right? So whenever we have a higher sum, we move the end pointer, because the end pointer is can point towards the decreasing sequence of number. And whenever the sum is more than what we require, then we increment the beginning pointer, the P1, because it is pointing towards the increasing sequence of numbers. So 7 plus 6 means 7 is more than 6. So we need a smaller sum, which means we should decrement P2. So let's say P2 comes here. Okay, I'll cross this. So now, in one iteration, we only increment or decrement one of the pointer, not both together. So now we are pointing at 1 and 4. So 1 and 4 is 5, and 5 is less than 6. So we need a higher sum now. So higher means we increase our P1. Let's call it P1 over here, and which means now we should have more sum, which is again pointing out towards 4 and 2, and 4 and 2 is 6. That's how we find out our you can say target sum. So this approach, as you can see, ensures that we are only actually finding out the exact pair that can lead us to our solution. And if there is no other, I mean, the smart way in which these two pointers move, they ensure that you never miss any number. Whenever the sum is increasing, sum has increased more than, or sum is more than the target number, we try to decrease the sum. And if it's less than the target, we try to increase the sum. And we will try to see all the intelligent combinations and try to find the pair that we are looking for. So that's the idea about this approach, in which we smartly use two pointers, and the overall idea is use one pointer from the start and the other from the end. And as you can see, we iterate this whole array only once, which means we actually traverse each number only once, or you can say one of the pointers, they pointed out to these numbers, and they only point out to one number at a time, and they never actually come like we can finish this search as soon as the pointers are equal or they cross each other. I mean, as soon as they're equal, we can be done. So which means every number is only pointed out by one of the pointers once. So which means we are iterating the whole array only once, which means the time complexity is order of n, without any space. So this is the most efficient solution, you can say. As we'll see, more variations of the two-pointer approach, we'll get a better feeling of this algorithm, this approach, this technique. But I mean, from this very easy problem, we got this idea that, oh yeah, we can easily use two pointers to iterate the array and solve the problem. Let's see the solution. Yeah, over here we describe the same thing. Can I decrease the darkness? Yeah, okay, let me see the next time. I'll try to use the harder pen. Okay, let's see the solution. Okay, let me try the pen here. So the same problem, and let's see. Let me increase the font size so a little bit. Okay. Can you guys see this fine?
Yeah.
Yes. Yeah.
Okay. So very simple. Again, we can quickly do it. This is the method. This is the given array, and this is the target sum. Okay. We use two pointers. We call it left and right. Left is pointing to the first number element, and the last is pointing out at the last element. Right. We keep iterating until they are equal. As soon as they are equal, they are not pointing out add two different elements, so the pair is not possible. As soon as they are equal, we can finish our while loop. And while loop is just this thing. And if we this whole while loop is trying to find a pair. If we don't find a pair, we return -1. So at any point, current sum is the left number and the right number plus, and if that number is equal to the required sum, we found our pair. Otherwise this is the if we discussed that if the target sum is more than what we require. Currently, this current sum is less than the target sum, so we need the higher sum, which means increase the left pointer. Otherwise, we need to decrease the sum, which means decrement the right pointer. So whenever we need a bigger sum, increase the left pointer. Whenever we need the lower sum, decrease the right pointer. That's the only difficult part in this question. As you can see, time complexity wise, we have just this while loop. That's why the time complexity, this whole while loop is in the worst case can iterate the whole, can iterate the whole array, you can say, because either we are increasing the left pointer or decreasing the right pointer. Anyway, we are traversing one number at a time, and at the maximum, in the worst case, when the pair is not there or the last element is the pair, we will end up traversing all the numbers. So order of n, and you guys can see there is no there's just constant space we are using. So order of one is the space-time complexity. Yeah, so it tried to explain a little bit more. Okay. What else over here? They have discussed an alternate approach. An alternate approach which is actually not a two-pointers approach, but it's a good idea to actually understand this. Let's quickly jump onto the code. If you see, what are we trying to achieve here? We are actually using a dictionary or a hash map, you can say, hash table, right? Where we are storing the numbers over here. It is actually a hash set, you can say, because we just need one number. So whatever we're doing, we are actually going through again all the whole array, and at any point the target sum, which is the required target, and the number we are iterating, we minus that, and the number that we find out, if it's already there in that dictionary, this means we have already traversed that number before, and then we can return that. The idea is, like, for example, when we are here, when we are, like, let's say at number 1, what are we doing over here? Return. We are actually, yeah, it's a hash table. So what are we doing? That the number we are iterating, we need to find the other number, right? The pair. So we actually push the current number in the hash table, so that later on, if we need this number to make this pair, we can quickly search it up. Again, it's this algorithm would be order of n because of this for loop. And because of this hash table, it would need order of n space 2, because we are pushing each number in the hash table too. So it's not efficient than the two-pointers approach, but it generally tells you something. It teaches you something that, oh yeah, since we, instead of searching the number, for example, in the binary search case, we take one number and search in the remaining array. Over here, we say 1 and we try to see the other number that we have already traversed or not. Like 1 is there, so we need 5. So try to see if we have already traversed 5 or not, and 5 should be there in the dictionary. If not, then we move on to the 2. 2 and 2 minus 6 is 4. Try to find 4. There's no 4 we have traversed, so move on to 3. 3 minus 6 is 3. Try to find if we already traversed 3 or not. 4 minus 6 is 2, or 2 is already there. So we found a pair. This is, you can say, we are getting, we're not using the binary search, but using a data structure like hash table to store the numbers that we previously traversed. Generally, so this approach would work even if the array is not sorted. So you can actually compare it with that problem, that if the given array is not sorted, then I think this approach is the most efficient approach, because if the array is not sorted and we need to find the pair, the one approach could be the brute force approach is again n square. The binary search won't work, so we can sort the array. So the sorting the array would be n log n, or an order of n space if we use that kind of search. So n log n, and then we can use binary search n log n. So that algorithm would be overall n log n if the unsorted one. But this algorithm would be order of n time and order of n space, which is considered better than the n log n and order of n space. So if the array is not sorted, this approach is the most efficient one. But if the array is sorted, then the two-pointer approach is the most efficient one. Overall, I think you can always assume three kinds of solution with arrays when you wanted to traverse the array. One is, we have the array and we can do this brute force thing, which is n square. Then we can always use sorting plus binary search, and which will give you generally order of n log n. And then if there is then this kind of approach where you use order of n space, but order of n, like order of n time complexity, but order of n space. So three solutions can generally be, you can always actually come up with this three kind of solutions in most of the cases, and see which one works better. Or the binary, the true pointer approach is even efficient, which comes in a more smarter approach. You can the first three approaches, you can consider them as brute force approach. All right, any question or comment? Yeah, this was pretty straightforward. So let's do a little harder question. Yeah, so this one, which is, given a sorted array, create a new array containing squares of all the numbers of the input array in the sorted order. So we are given an array and we need to find the squares of all the whole array. The array is sorted, and we expect that the squares are sorted too. For example, this one, this input, if you see, so the problem over here is like this can be squared easily, 0, 2, 3, but then since negative numbers can produce positive squares, which will mess up the whole array. We cannot really sum every element and produce the output array. So we need a smarter way. If you see, 0 is already there, okay. This 1 comes from squaring this number, and these two 4s are, one is from the positive 2 and the other is from negative 2, and the 3 comes from, and the 9 comes from the 3. So overall idea is, we can, we cannot really straightforward sum it up, some numbers, and produce the numbers in the sorted way, because of the negative numbers that is causing the issue. Let's see. Yeah, so we can actually use two approaches. Let me share. Let me try to solve this thing over here. So select all, and then what? How do I delete this thing? Okay, so what was the thing? -2, -1, 0. Okay, -2, -1, 0, and 2 and 3. Okay. So one approach could be that we know that, okay, if we try to square these numbers, then it is fine. But then these numbers, the negative numbers, are causing all the issue. So why not, since this array is sorted, why not we find out this middle element, this point where the array can be broken into positive and the negative numbers, right? So which means we can have one pointer pointing at 0 and the other pointer pointing at -1, right? So these two numbers will be producing the smallest sum, right? Because both of them are 0 is the smallest, there's a smaller positive number, and -1 is the small is the bigger actually negative number, but will decrement over there. So 0, 1 means, okay, this could be P1 and this could be your P2. So which one produces the smaller sums? P1. So we put 0 in our output array and increment P1. So P1 is then pointing towards over here, right? So now -1 and 2, which one produces the smaller square? 1. So 1 over here. So we'll point P2 towards 2. Now 2 minus 2. So which one produces? They both produce the same number. Let's put 2 4s over here and then increment this over here, and this will actually not go anywhere, and 3 will produce the 9. So overall idea is try to find that where the numbers are converting from positive to negative. We can iterate the array as well, order of n, or we can use binary search, and then use two-pointer approach to smartly find out the smaller sum and populate the array from the populate the array based on the 2 pointers, whichever gives the smaller, and we can increment decrement pointers based on that. It's again very straightforward. The other approach is that we discuss is this one. Oh, yeah. So -2, -1, 0, 2, and 3. This was it. The other approach is instead of finding out that the place where we're converting from negative to positive numbers, we can actually use 2 pointers. One is over here, P1, and the other is P2. So these 2 pointers can always produce the biggest square of the output array, you can say, right? So -2 or -3, which one produces the bigger square? 3. 3 produces 9. So try populating your output array from the end then, okay? Because now we are getting the biggest square. So we put 9 here and move P2 to over here, okay? Now though both of them pointing to the same kind of square. So 4, let's move here, and 0 -2, 4. So 4 over here, move P1 over here. So -1 or 0 means 1 will be the bigger. So 1, and then yeah, we can increment it over here, and then finally 0 will come here. So we can use both the approaches. Either we can take the highest square first and populate the output array from the end, or we can use the binary search method and use it. Any question? Anyone has a question?
No.
Hello, are you saying something?
Sorry, my microphone is up. Sorry.
Okay. Okay, so we can jump onto the code. So these two approaches we have explained over here as well. You can if you want to read, you can read about it. Let's see the code. This is again pretty straightforward. Over here we are saying we have the n numbers, and then we created the output array, put zeros over there. Highest square index. Okay, by the way, we were following the second.
Sir, I have, if array is not sorted with having both positive and negative numbers, keeping the highest squared in the end would not work, right? Because my middle of the element produce highest square, then how can we upfront decide we can keep it the end of the element.
Yeah, if the input is not array is not sorted, this won't work. So we are trying to solve this question when the array is sorted. Do you want to repeat your question?
Yeah. So when array is not sorted, you cannot decide keep your squared value in the end when with the 2 pointers.
Yeah.
Then the 2-pointer approach would not work here, right?
Exactly. It won't work.
Then we are going back to binary search.
Binary search,
sorting.
Sorting. Yeah. First, you have to sort the array. I don't know what could be the solution over there in that case.
Or can't we do like HashMap and search the element and trying to square it up? Then you don't need to put end of the highest squared value in the end or middle. Does not matter, right? All I need to square the value.
You can square, but then how would you sort them? The main idea is the numbers are unsorted. You can square each number, but how would you produce the sorted output array? That's the main challenge in that case. Yeah, and sorting cannot be better than n log n, right? The comparison-based sorting. The other, the count sort or radix sort kind of thing, they have some limitation. In this case, like, yeah, I think if the array is not sorted, then of course we have to go back to our older solutions and log n. And then at that point, I think this problem is not interesting. I would not ask it in the interview. It's only interesting when the array is sorted, and then you will try to find this stuff.
Maybe an interviewer might trick a person to give unsorted arrays and do this act. Maybe it's a counter question to ask.
Exactly. If they really want to, if this guy has memorized a solution or not. Yeah. Okay. So this index is, we're using the second approach, by the way, where we are taking the highest square and populating the output array from the end. So highest, how can I move it? So the highest square index is the index in this square array. Okay, we use 2 pointers left and right, and we keep doing it until they are equal. In this case, we have to go with the equal because the last number needs to be squared as well. We find out the square of both the numbers and see whichever is like bigger. Whichever is bigger, we put it in the output array. And if it's left side, we increment the left side. If it's the right side, we decrement the right side. And then since we have put the number in the highest square index, we decrement because we're populating the output array from the end. So we decrement over here. We keep doing it until left and right are equal or they cross each other, right? And then we return the square. Solution is very simple. The code is quite simple. It's just that approach that you know, as people call it, the aha factor. You really figure out, oh yeah, if I use 2 pointers and from the 2 ends, and they produce the highest square. So populating the output array is very easy in that case.
Yeah, while you're explaining, it seems like everything is baby algorithms, but it's not when we write it.
When you write in the code, yeah, I mean, definitely, it's during the interview setting, everything is difficult, you know. Yeah, you have to practice write the code a lot, especially with these problems. As I used to tell a lot of people, like there are these certain algorithms, for example, the binary search one, or this is the generic template for the 2-pointer, right? There's a while loop from left to right, and you are incrementing it. So these kind of solutions should be in your head all the time. Binary search or the breadth first search, the depth first search kind of solutions, you should be efficient, so quick you can, I mean, as I call it, should be able to write them with your eyes closed. I mean, because in the interview setting, you wanted to save as much time as possible and don't want to make silly mistakes. Binary search is like very easy, but it has those indexes playing, and then, okay, I'm incrementing or decrementing, or middle is where. So those kind of things need to be like right in your head when you're going into this exam. Interview is more kind of an exam over here. Otherwise, yeah, it should actually. But anyway, that's the idea. And if you keep writing the code, you will get better with it. It becomes very quick in the interview setting.
Yeah, thank you.
Order of n space and order of n time. As we can see, the time is order of n, space is only because we are using this output array. If you don't consider the output array, then we are using constant space. We are not using any auxiliary space to produce the final output. The final output only required the space. All right. Again, very easy. I think both these problems were quite easy, but you get the idea of the 2 pointers. So far, what we have learned, the arrays are generally sorted. When they are sorted, we can definitely use binary search in some way. We can use 2 pointers as well, and most of the times the 2 pointers are pointing at both the ends of the array, and then we smartly decrement and increment these pointers to solve the problem. All right, let's do a couple of more questions to get more feeling with this pattern. Yeah, these are all similar. Dutch national flag is quite famous problem. I don't think people will ask now, but you can actually learn a technique in this problem. It has 3 type of elements, and then you use kind of 2 pointers approach with the 3 types. It's a must do. What else? String containing backspace. That's an interesting problem, and yeah, it's a medium problem. So let's do the previous one we did was medium 2. Squaring a sorted, it's an easy one. Okay, let's do a medium one, little difficult. Strings containing backspace. Okay. Given 2 strings, let me make it a little bit. Given 2 strings containing backspaces identified by the character hash, check if the 2 strings are equal. The idea over here is we have these hashes, and this hash means a backspace, which means the previous character should be gone, right? So if we like execute this backspace, this hash should get rid of this y, and the string becomes x and z. Similarly, this hash should get rid of this z, and we are left with xz as well. So they wanted to see if the 2 strings are the same. But we cannot really compare them right away because they have these backspace characters, and backspace characters can should actually remove the previous element. Over here, if you see, if you execute this hash would take y, we are left with xz, and this hash would take z, and we have xy. So xy is not equal to xz, so false. Similarly, over here, hash would take away p, and these 2 hashes will take away z and y. So we both are left with x and x, so the strings are same. So this last example is also telling us that there can be multiple hash signs, multiple backspaces together. So we cannot assume that there's only one backspace, or I mean, they can all come together, and then we have to get rid of these many characters in the previous indexes. Okay. So we can actually use the same a similar 2 pointer approach, and the idea over here is let's iterate from the back, because if you try to iterate from the beginning, for example, let's say over here, if we're trying to iterate from here and here, we don't know that, oh, this character will go away or not, because I mean there could be a backspace right after it, and this would be going away. So trying to compare from the beginning of both the strings is not possible, because we don't know if that character is going away or not. But if we are trying to compare it from the back, then if there is a character, they should match. And if that character is not a valid character, means it is a hash sign, then we get rid of those many characters based on the hash signs, and then go to the next valid character, so that we can compare it with the next valid character of the other string. What I'm trying to say is over here, let's say over here, we pointed out both at hash signs. So which means we need to get rid of the next character, right? So this hash sign would take away the p pointer, and then it will point out at this index, right? Index 1 would be over here. Whereas these two, which means we can count hashes and get rid of these two characters and point over here. And so means index 2 and index 1 both be pointing out at two valid characters. And at that point, we'll compare these two characters that they should be same. Otherwise, the string is not same. If they're not same, we can return false. If they're same, then we move on to the next valid character. And valid character is always, as I said before, we will get rid of all the hashes and the characters the hashes are removing and move on to the next valid character. That's what they're trying to do, this and this. They remove the, the two hashes that keep removing, and then they came here, and over here they said, oh, both the characters are pointing out the same character, both the pointers, and we found and we returned true over here. So you, overall, I think the idea is there's no sorting over here. These are strings now, and the idea is we cannot compare these two strings from the beginning of the strings because of the nature of the backspace execution, you can say. So overall, I think the one heuristic is, like, I always try to see if you can iterate the string or the array from the back, or in the previous case, we did two pointers within the same string, but we used we populated the output array from the end, right? So going from the end sometimes solves a lot of tricky situations. So that's the learning, you can say. So this should be in your head. Okay, let's quickly see what's the code look like over here, and I'll use the yellow one. Two strings we have, and the two indices, index 1 and index 2 indexes, string 1 and string 2. Both of them are, the while loop is if any one of them, either there's an OR sign, which means, right, so both of them should go to the 0th index and we'll match everything. And if one of them goes to 0 and the other one still has some character left, that means the strings are not equal, right? So that's why there's an OR sign. You cannot have an AND sign. If you put an AND sign over here, then one of the index could go out of the bounds. So this OR is important. So over here, we're calling this auxiliary method called next valid character. It's that algorithm that I was trying to tell. So let's actually go through this algorithm to see how they are calculating the next valid character. So it is passed the index at current index you are, and this is the string. So in this string, we are at this index, and we wanted to see if the character at this index is valid. If it's not valid, then give me the valid character, right? So as we said, the tricky part was there could be more than one backspace. So we actually started a local variable called backspace count. So if its index is greater than or equal to 0, which means we have more characters left to process. If it's a hash sign, which means, oh, it's not a valid character, so just increment your backspace count so that we can get rid of these many characters. And if it's not a backspace character and it's a valid character and the backspace count is greater than 0, we also need to see that, oh, it's a valid character and there are backspace counts available, so consume this character with the backspace, which means decrement the backspace count. So increment the backspace count if we have got the hash, and if the backspace count is more than 0, decrement it because we want to get rid of these many characters. In the else case, which means it's not a hash and it is a it is a valid character, and the backspace count is not greater than 0. It's 0. So we should break that, or we are at this valid character. At that point, we can return the index. What is this thing doing? This is just the decrementing the index. We can have a for loop as well over here. So overall, the index that is iterating the string. Is there any difficulty understanding this algorithm? All right, I assume you guys understand everything. So yeah, so now if you see, we have the two strings and we got the two valid characters pointed out, two valid characters on those things, on those two strings. So I1 and I2 now are pointing to towards two valid index, two valid characters. So this condition means reach the end of both the strings. If you can see over here, we are decrementing index, right, in both the cases. So imagine we are at the 0th index of both the strings, and so or we right. So 0 was it was the last valid character. So you decremented, it becomes -1. So you returned -1 actually, right? So this means this condition would be true in that case, which means we have reached the end of both the string. So if I1 is less than 0, which is -1, or I2 is less than 0, then we can return true, that or both the strings match. If not, if one of them is 0, which means, oh, we have reached the end of one of them and the other one is still left with, it's not 0, so we can return false. The strings are not matched. Otherwise, now we are pointing out two valid characters, right? So which means they both should match. If they don't match, return false. Okay. So these three ifs are actually a little tricky, but they're solving the core of the algorithm. If we reach at the end, which is both the index will point out at -1, we can return true. If any one of them is pointing out at -1, which means, okay, one has more characters than the other, return false. Otherwise, we are pointing out at the valid characters, they should match. If they don't match, return false. If they match, then none of this if will go through, and which means we have successfully matched two strings. So now update your index 1 and index 2 to the next valid character, or the probable next valid character, which is I1 -1, because the I1 that returned by the function, we already matched. So now we are pointing out to the next character, which could be valid or not valid, and we go back in the while loop over here and pass the index 1 again to this auxiliary method to find out that oh, this character is valid or not. Go through this thing completely again and again. Any question? Over here, so if you see what's the time complexity, so what is the time complexity of this algorithm? So there's this while loop, which is, of course, it looks like we are iterating two strings, so we will iterate both the strings. So order of m plus n, you can say m is the length of one string and n is the length of the other string. But this while loop, would it cause any issues? Would it increase the time complexity? Anyone has answer to this thing? So because we are calling this while loop twice over here, this function twice, and it's actually, it has a while loop in it. Would it cause any issue? Would the time complexity still be order of n, or it's more than order of n? No one has the answer. What do we say here? It should be order of like m plus n. It should not increase, because you can say this index is decrementing, and we pass this index to this function, and this index gets decremented, which means it is processing some number of elements, right? And that is the same index. Same index is used in the while loop. So you can say that there are two while loops, both are decrementing the same set of indexes. And so overall, this while loop and this while loop and the other while loop, they're actually using the same string and same index, and the same index is getting decremented, and we don't increment or decrement these two indexes separately. It's the same number that only iterates through. It's the same index that iterate the whole strings, the two strings, and they do it exactly once. This assignment is also telling us the same thing, that the index that was returned, although because this while loop might have traversed some numbers, so we have to skip those numbers for this while loop. So that's why this index one, if you see, this index is not getting incrementing or decrementing anywhere. It's only being used by the two index returned by this while loop. So this while loop is actually decrementing the numbers. Okay. Did you guys get it, or it was too difficult?
Makes sense.
Yeah. Okay.
Just to verify, there is another solution to this problem, right? We can use, I know we are discussing 2 pointers here, but if you're moving forward, then we can also use stacks, right?
You can use stack. How come? What could be the algorithm?
So basically, you have one pointer in string 1 and the other pointer in string 2, and then you move forward. And then wherever a hash comes, you keep appending to the stack. Whenever a hash comes, you pop from the stack, and in the end, you compare the two residual strings, whatever are on the stack.
Yeah. Interesting approach. Yes. So we trade one string, keep pushing in the stack. As soon as we see the hash, we pop it, and so we have a valid string left. So in that case, you are using auxiliary space, though.
Yeah.
Right. So the time complexity would be order of m plus n. But the space complexity would be order of m plus n as well. So so there could be an alternate approach, which is a very interesting approach, actually using stack. The only thing is it's using probably that would be more cleaner because of the stack push and pop, but it will definitely use extra space. Yeah. But thanks for pointing that out. It's a great approach. Yeah. All right, so let's do another thing called minimum window sort. So it is actually a hard problem. It's a medium problem too. Yeah, that's good. It's an interesting problem. I actually once got this problem in the interview, and it was very difficult for me. There was this small point I would like to emphasize over here in this solution. Given an array, find the length of the smallest subarray in it, which when sorted will sort the whole array. Okay, so the given array is not sorted, and we need to find a subarray, which is the smallest subarray in it, that when we sort that subarray, the whole array becomes sorted. Very interesting and very different kind of a problem. So output is 5. What are we outputting? We are number of elements, I think. Yeah. So what is the explanation over here for this? So 5, 3, 7, 10, 9 is the, so 5, 3, 7, 10, 9. So 1 and 2 are in their correct positions. They are the smallest two numbers, and they are in the sorted order. Similarly, 12 is also sorted. It's the highest sorted number, but 9, 10, and because 5 should be after 3 and 10 should be after 9. So that is why it's this whole section needs to be sorted to make this whole array sorted, right? So we need to find this you can say this smallest subarray that makes the whole array sorted. Over here, it says 1, 3, 1, 3, 2, 0, -1. Yeah. right? So the 7 and 10s are in the sorted place. They are the two highest number in the sorted order, but the first 5 numbers, they are not sorted. So we need to find that. Similarly, 1 to 3, they're already sorted, so return 0, and 3 to 1, although they are sorted in descending order, but we assume it's asking in the ascending order. That's why nothing is sorted. So we need to sort the whole number. The whole array needs to be sorted. So, how can we solve this thing using the 2-pointer approach? Like if we use, I'm just brainstorming over here, right? If we use 2 pointers, or actually use just 1 pointer at one at a time. Let's use 1 pointer and see if everything is sorted from the end. So 12 is sorted, 9 is sorted, because 9 is smaller than 12, you can say. But as soon as we reach 10, we say, oh, 10 is not at sorted place, because they should swap. So we can say the array is sorted till then, but then, okay, 1 is tricky. Similarly, we try to do here, 1 is sorted, 2 is sorted. Sorted means it's bigger than the previous number. 5 is again sorted because 5 is bigger than the previous number, but 3 is not, right? Because 3 is smaller. So can we say that 3 to 10, if we sort it, can we say that 3 to 10, if we sort this subarray, this will sort the whole array? As you can see, we cannot say that, right? So we use 1 pointer to see how many numbers are sorted from the end, and then we use another, we iterate it again from the beginning and see how many initial numbers are in the sorted order. But the subarray that we found out is not the subarray that when we sort it, it won't sort the whole subarray. So whole array. So what is causing the problem over here is that for example, this is the biggest number and this is the smallest number. 3 is the smallest number of this subarray, you can say. So which means this 3 should go like at its correct place, which means we need to expand this subarray to include all numbers that are bigger than 3, because at that point 3 would be in the proper place, and then that subarray would make everything sorted. Similarly, 10 over here, so we need to move on the right direction and include everything which is smaller than 10, because that would come before 10. So we need to expand this subarray in the second step and see, what is the smallest number in this subarray, and include everything on the left which is bigger than the smaller number, and similarly include everything from the right which is smaller than the biggest number. So that biggest number could be anywhere. The 10 could be over here, 10 and so first we find that small subarray that should be sorted, but then we'll find the smallest and the biggest number in that subarray, and then expand the subarray based on this condition. So this last thing that I was trying to explain, this was the thing that eventually I came up in the interview, but it took me a lot of time that to understand, okay, yeah, I need to expand it back because the sortedness is screwed up if we have like smaller numbers in the subarray or the bigger numbers from the end. Let me see how we try to explain it. Yeah.
Can you explain the second use case with the same algorithm?
Yeah. So let's see over here, right? In this example too. So 1 is sorted, right? 3 is sorted because 3 is bigger than 1 because they're ascending, but 2 is not, right? Okay, so from 2 we don't have some. So over here 10 is sorted, but 7 is sorted because 7 is now smaller than -1 is sorted, because -1 is smaller than 7. 0 is not. 0 is bigger than -1. So we can say this is our subarray that should have been sorted. But then when we saw that, oh, so there are other numbers that should be included in this thing. Now the expansion comes. Though find the smallest number, which is 0, and include everything on the left, which is which makes this 0 at its correct place, right? So anything bigger than 0 should be part of this sorting process. So 3 is bigger, 1 is bigger, and 0 should come over here, right, somewhere. So we will expand our, let me use the other pen. So we'll expand our this array, let me call it black, till here. Similarly, this 2, which is the biggest number, and try to include everything, because the 2 should go at its proper place. So any number which is which is bigger than, which is smaller than 2 should be included, because 2 is bigger and 2 should go its correct place. In this case, actually, it's tricky because we just want to include. So -1 is smaller than 2, so we should expand till here, but 7 is not. So which means, 7 and 10 are fine. So our whole array would be this one, -1, 3, 2, -1.
Should we find the bigger number and smaller number in the subarray, and then we have to extend?
Yeah. Yes. We need to find the smallest number and the biggest number in the subarray that we have figured out yet, and then include everything from the left, because that smaller number is dictating that, this smaller number is somewhere on the left side. So anything which is bigger than the smaller number, include it in the subarray as well, right? And with this biggest number of this subarray is telling us it should be somewhere on the right side, because all the bigger numbers on the right side. So include everything which is smaller than this bigger number, because at that point this bigger number would be at its correct place. So that's how we expand this subarray based on the minimum and the maximum number of that subarray.
Yes, thank you.
Yeah, that's the tricky part. Interesting thing, actually. I think once you learn it, it can be used to solve many problems, actually. 110, 110, 310. Yeah, they're doing the same. Let's see. So over here, 10 and 7 are sorted. 1 and 3. 1 and 3. 3 should be sorted, right? I don't know why they include this. Might be a mistake. So 2, 0, -1 should be the thing, because 1 and 3 are in the correct place. Similar, and then they said they find out the max and min. Max is 3 and min is -1. 3 and -1. Yeah. So, and then they expand it based on that. Yeah. Since they made a mistake over here, I'll get it corrected, actually. Let's see the code. We used low and high pointers, 2 pointers. Okay. And both low is less than the array length, and find the first number out of the sorting order from the beginning, right? So this whole thing is, of course, we are incrementing low, and till we see low is equal to the next number, or low is smaller than the next number, because we see from the beginning it's all ascending, from the end it's all descending. So this part is ensuring that we are finding all the ascending numbers. If we keep finding ascending numbers, keep incrementing the lower part. This is just a check if we reached at the end, which means the array is already ascending, everything is fine, so return 0, means there's nothing to sort. Now we are doing the same thing from the end. Everything should be in the descending order, right? So this number and the previous number, they should be the high number should be higher than the high -1. So this is the descending side, keep decreasing. So after these two while loops, this one and this two, we now point out that we find out that probable subarray that can be sorted. Now we need to find the min and max of that probable array and then expand it. Let me see this thing over here. Yes. So, so this is just the two variables, infinites. And then we went from low to high. It's that subarray that we found out, and find the max and min of that subarray, right? After this for loop, now we have the min and max, or the maximum or the minimum number of that subarray. And now we expand it. And as I said, since we need to now decrement low, include everything which is like bigger than the smallest number, right? The subarray min. The subarray min has a small number. So anything which is bigger than the smaller number, include it into the low. And why? How we include it? We decrement low, 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 low. Similarly, over here, we increment based on if there are smaller numbers than the subarray max. So yeah, if you understand the logic I was trying to explain, these two while loops are pretty straightforward. And in the end, return high minus low plus 1, which is the length of the array after the expansion, which should be sorted, which should be sorted to make the whole array sorted. All right, so any question or comment? Okay, this is order of n, this could be order of n, this could be order of n, right? Yeah, everything could be order of n. Even this for loop could be order of n, this while loop could be order of n in the worst case and is worst case, but all of them are parallel. They're not cascaded while loops. So we can say the overall time complexity of this algorithm is order of n. You can say first you're iterating from the front and the back, and you cannot iterate more than like n elements in this case, and then you expand the subarray. So at that point you are iterating some elements twice. So in the worst case, time complexity could be order of n plus n, which is 2n, and which is order of n, asymptotically speaking. It's not n squared, it's 2n, and 2n is considered an order of n. Is that we have written over here, order of n, and yeah, constant space. Okay, yeah, I think that's pretty much it. We have gone through 4 problems, 2 mediums and 2 easy. This is overall the 2-pointer approach. Very interesting, and it should like open up a lot of scenarios. This last problem was a little more tricky, although we're using single pointer at a time. You can say expanding or like shrink in the beginning and from the end. We're trying to find a subarray, then we're expanding at one pointer at a time. But you can say it could be a sliding window approach as well. You know, I don't know if you call it, but we have a window, and that window is not sliding, we are incrementing. So yeah, probably 2-pointer is still that thing. But the idea is you use 2 ends, 2 pointers or 2 ends of 2 ends within an array, and try to expand or iterate those numbers through those pointers to solve the problem.